Now, I do not have a good answer for really what secant, cosecant, and cotangent are used for. I need to look into that more. But sine and cosine, very helpful. The graph of tangent, not so helpful, but tangent itself as a function, very helpful. If you're solving a triangle, you'll use tangent lots of times. So all three of those have a lot of application in the real world. I am not certain why one would need to use secant, cosecant, and cotangent, but they are definitely always in, I mean, this is not new. I've taught it since I've been teaching Precal. So they're out there a lot. So I'm not exactly sure why, but they're there. So we're going to learn them. And they're not terribly difficult necessarily. Secant, cosecant, and cotangent are also sometimes called the reciprocal functions. Anybody remember what that word reciprocal means? I wouldn't say opposite, because opposite a lot of times means like the negative of something, and so it's not negative. Not really. Another time you'll hear the word reciprocal is like when you're dividing fractions. It's the flip. It's a flip, right? So the reciprocal is the flip of the fraction. I just always say dividing fractions easy as pie. Flip the second and multiply. But if I wanted to be much more refined, I could say that you need to multiply by the reciprocal, right? So that is going to be when you flip that fraction. So secant is 1 over cosine. So we take just the cosine function, which would be like cosine over 1, right? We flip it upside down. Cosecant is 1 over sine, and cotangent is 1 over tangent. Okay. To keep these straight, I remind myself that there needs to be a co in every pair. Now, it does cotangent and tangent go together. That seems right. It feels like sine and cosine should go together, but they do not. Whenever we're thinking about secant and tangent, secant and cosecant, secant is going to have to go with cosine, because secant doesn't have a co, right? You can't have two co's together, and you can't have two things without a co together, right? You have to have one co in each pair. So like you got cotangent and tangent. So cosecant has to go with sine because it already has a co. It can't go with cosine. You can't have cosecant and cosine together. So one co per pair when you're thinking about those reciprocals. That helps me remember, because when I think of secant, I know it goes with sine or cosine. It has to be cosine because you have to have a co there. So these are going to be things that we have to have memorized. Tomorrow we will start into looking at different trig identities and manipulating functions. So these are 3 things that you'll need to have memorized for that. So the graphs of these are crazy. I don't think we're going to have to do a lot with the graphs, but we're going to have to do some. Okay? So the graphs of each of these reciprocal functions will include vertical asymptotes whenever the denominator is 0. There. And this is important because I do not expect you to have these graphs well memorized at all, because they're kind of crazy graphs. But what I do expect is for you to have the sine and the cosine graphs memorized, right? Like we've written that out a lot of times. You guys are pretty good. If I ask you to sketch out sine or sketch out cosine, you could probably do that for me now. Yes? Correct. So if you have a denominator of 0, the value is undefined, which gives you a vertical asymptote whenever you're graphing, because there's not going to be actually a value right there. So the graph of secant, see this dotted line in between right here? This dotted line is not part of the graph of secant, okay? What is that the graph of right there? Not sine. Its y-intercept is right here at 1. That's cosine, right? So this is not part of the graph, but Mr. Passwater has put this in here, right? Because secant equals, oh, it's doing this weird thing, 1 over cosine of x, right? So, anytime cosine equals 0, see like right here, or here, or here, or here, right? I've got a vertical asymptote. So whenever you're graphing secant, the graph of cosine with all the same properties, same period, same amplitude, all those things should fit like in between there. Okay, and if you think of your unit circle, cosine is your x-coordinate. Your x-coordinate equals 0 right here at 0, 1, right there, and right here at 0, negative 1, right? So if we're doing secant at pi over 2, secant of pi over 2 would equal 1 over 0, which is undefined. There. And so at pi over 2, you can see vertical asymptote right there. In a similar manner, cosecant is 1 over sine x, right? So everywhere that your sine graph equals 0, you have a vertical asymptote for that. So anywhere sine equals 0, you'll have a vertical asymptote. For your vertical asymptotes for secant, the first place where cosine equals 0 is at pi over 2, if we're thinking about the unit circle. But how often do these repeat? How far apart are they? It's every pi for that. So the period for cosine is 2 pi, but cosine equals 0 twice within that interval, right? So like from here to here is half of the circle, which is pi, and then back up to here, which is half the circle, which is pi. So we can say that the vertical asymptotes are at pi over 2 plus pi k. And for sine, vertical asymptotes, we can think of for sine, the first time that sine equals 0 is right here at 1, 0, right? At 0. So we could say x equals 0 plus pi k. But do we really need to put the 0 there? Not really. So we could say just pi k. And both of these are where k is an integer. We're going to see some more problems where we got to talk about the asymptotes. I really think about it from the sine and cosine graphs, not really the secant and the cosecant graphs, because they're kind of complicated. But I do want you to see this picture. So if you see a graph and they're asking you something about it, and you see that it looks like these crazy U's with vertical asymptotes, it's either secant or cosecant. Those are what those look like. Mm-hmm.
For secant and cosecant, like all the other stuff like sin and cosine, all that stuff,
Mm-hmm.
like applications on the unit circle. Does it have any application on the unit circle?
It does, because it's just like the reciprocal. So, so like for example, like if you're finding secant of pi over 2, that is going to be 1 over the cosine, so 1 over the x-coordinate. So like secant, cosecant, cotangent, you can find those from the unit circle. So we could do something similar to what we did with sine and cosine, where we could take those unit circle values and graph everything, and we would end up with this graph if we did. They're less useful, these graphs, so we'll spend less time on that. But it is just like any of the values you can find from the unit circle there. Okay, now the ranges of secant x and cosecant x. So remember, ranges are our y values, right? What's our lowest y value we could possibly have on this graph? Negative infinity, right? So these graphs go all the way down to, why is it not letting me write and making weird? What have I done? I think I don't want this. I want my regular writing. I'll make that go off. I mean, I guess this will let me write. This is not what I want. Alright. Negative. Oh, exit drawing. Let's do that. Okay. I want the regular pen I usually use. Okay. Negative infinity. 2. Now, does it go from negative infinity to positive infinity? There's a gap in the middle, right? Because remember that cosine graph's not part of this gap. There's a gap in the middle. So we go from negative infinity up to, what's the highest value we have on these like lower pieces? Negative 1. So we go from negative infinity to negative 1. We're going to use a bracket with that negative 1 because you do actually have some that equal negative 1. And then we have a gap. Where do we pick back up? 1. And then we go up to positive infinity. There. Okay, questions there? All right, cotangent is another crazy graph. Cotangent looks a lot like tangent, but your squiggles have been switched, right? So tangent of theta, remember, looked like this. You had like vertical asymptotes here at negative pi over 2 and positive pi over 2. And then the squiggles went like this. Cotangent looks a lot like tangent, but the squiggles are switched and decrease instead of increase, right? To me, I think it's helpful to think of this. It tells us up there that cotangent of theta equals 1 over tangent of theta. What else do we know about tangent? What does tangent equal? What? It equals y over x, right? Or we could call it sine over cosine, right? We also know that tangent, I'll write this here, tangent of theta equals sine over cosine. So, if cotangent equals 1 over tangent, tangent could be replaced with sine over cosine, correct? Those are equal to each other. So, that would be 1 over sine theta over cosine theta. And dividing fractions is easy as pie. Flip the second and multiply. So we can also say that cotangent of theta equals cosine of theta over sine of theta, or x-coordinate over y-coordinate, right? I think this is actually more helpful to think of than cotangent equals 1 over tangent. Okay, so if I'm thinking about where cotangent has vertical asymptotes, right? We're going to have vertical asymptotes when the denominator is equal to 0, which means we're going to have vertical asymptotes when sine of theta equals 0. Now, the reason I want to go back to sine and cosine is because sine and cosine are easier to think of from that unit circle, right? So sine is my y coordinate. Sine equals 0 here at 0, and also here at pi. And then again at 2 pi, and 3 pi, and 4 pi, and 5 pi, right? So I could say that cotangent has vertical asymptotes at x equals, we could do 0 plus pi k, or it would probably be better, they're going to just do pi k right here, where k is an integer. So when I think of vertical asymptotes, I think of tangent is cosine over sine. I need to know where sine is equal to 0 for that. If I'm thinking vertical asymptotes tangent, I think tangent is sine over cosine, where is cosine equal to 0 for that. What's the range of this graph? What's the lowest we go? Negative infinity. Highest? Positive infinity. Any gaps in between? Not on this one, right? We don't have any gaps. So this one's just negative infinity to positive infinity. Okay, so let's look at some of the questions you're going to get for this. We've got let f of x equal 3 secant of 2x. Which of the following is a vertical asymptote on the graph of f? Okay, the way that I like to think about these is I like to change them back to sines or cosines, right? So secant of theta is just 1 over cosine of theta. So f of x is 3 times 1 over cosine of 2x right here. And we have vertical asymptotes when denominator equals 0. Since this is a multiple choice question, I could just plug in my answer choices to see which one's going to give me a 0 in the bottom. So if I've got 3 times 1 over cosine of 2 pi, in unit circle, 2 pi is right here. What is cosine of 2 pi? That's 1. So that's 3 times 1 over 1, not undefined, not that one. Okay. For B, I would have 3 times 1 over cosine of 2 times pi over 2. And that 2 right there, I can put it over 1. The 2's can cancel, so this is really like 3 times 1 over cosine of pi. What is cosine of pi? Negative 1. Still not 0, right? Okay. Then I could try this. 3 times 1 over cosine of 2 times pi over 4. And I'm going to put that over 1. That's going to give me 2 pi over 4. That reduces to 3 times 1 over cosine of pi over 2. Now, what is cosine of pi over 2? 0. Right here it is. That's going to be our answer for that. And then we could check D, it's not going to work. Okay. We can do something similar with example 2. Right? I've got cosecant. Cosecant is going to be 1 over sine. So really the 1 over sine part is the only part that really matters, right? Because g of x is going to equal 4 minus 2 times 1 over sine of pi times x. So the only part that really matters for vertical asymptotes is that denominator. The 4 and the 2 really don't do anything as far as finding vertical asymptotes do, right? So really, I could just be checking sine of pi x. So if I do sine of pi times pi over 2, that is going to give me, sine of pi squared over 2. Do we know what that is? We know sine of pi over 2, but not pi squared over 2. This is not a unit circle value right here. Nothing reduces. It's not going to be that one because your values that give you 0 definitely come from the unit circle, right? So it's not going to be that one. I could also try this one, sine of pi times pi, and that would be sine of pi squared. Is pi squared on the unit circle? No, not it. So the ones that have pi in it are out. I could do sine of pi times 1/2, which if I put the one on the bottom, I've got sine of pi over 2. Now, sine is my y-coordinate. What is the y-coordinate at pi over 2? Sine's y-coordinate 1 right here. So this is 1, still not a 0 in the denominator, right? Not this one. Let's hope it's D. And if I do sine of pi times 1, well, that's just sine of pi. What is sine of pi? That is 0. So D is going to be your answer because it's going to give you a 0 in that denominator. So even though secant and cosecant are new, I just turn them back into things that I know better, which are sine and cosine for that, to answer those questions. Okay, 3 is asking about range of cosecant. For secant and cosecant, we got all those u's, and we had that gap in the middle that went from -1 to 1, right? So what's going to happen here is when I multiply this function by 3, that is a vertical dilation by a factor of 3. It takes all of your y-coordinates, which is range, right, and multiplies them by 3. So the answer cannot be A, because this would be just for regular y equals cosecant of x, right? That would be the range for cosecant that has not been stretched out, right? But this is helpful. If I am doing a vertical dilation by a factor of 3, that means I'm going to take what the range was and I'm just going to multiply everything here by 3, right? What is 3 times negative infinity? Still negative infinity. Then I'll get a -3, a +3, and another infinity, right? So C is going to be your answer for that. That 3 is not necessarily called amplitude, but it's the amplitude of the sine function that goes with it, so it makes that gap wider. There. Okay, now we've got cotangent, and they're asking us to find vertical asymptote here. I would do the same thing that we did for the first functions asking us about vertical asymptote. We don't know cotangent that well, but we do know sine and cosine much better. So we said earlier, cotangent is 1 over tangent, but that's less helpful because tangent's also not on the unit circle, right? We have to think harder on that. So I would use that definition that we had that said cotangent of theta is cosine theta over sine theta. And so, I really only, in this case, it's going to be our k of x is going to be -5, and then you'll have cosine of 2 pi x and then that'll be over sine of 2 pi x, like that. So I'm changing cotangent into cosine over sine. And so what's the only piece here that affects our vertical asymptotes? Not all of that. Denominator. Denominator is the only thing that affects your vertical asymptote. So all you really care, you want to know where does denominator equal 0, right? Because the numerator can be 0. That's fine. 0 over a number is okay. But a number over 0, no way. We can't do that. So I'm just going to plug in what I've got. 2 sine of 2 pi x and see if I get 0. So if I do sine of 2 pi times 1/4. That's over 1. That will be sine of 2 pi over 4, but that will reduce 2 pi over 2. Okay? Unit circle. Pi over 2. Here my coordinates are 0, 1. What's sine of pi over 2? It's 1. It's okay. That can be an answer. That can be a value. That's not a vertical asymptote here. Let's try the next one. I'll have sine of 2 pi times 1/2. And I can put that 2 pi over 1. That is going to give me sine of just pi, because the 2's can cancel each other out here. And at pi, my coordinates are -1, 0. So what is sine of pi? That's 0. This is your answer because your denominator would equal 0. And when your denominator equals 0, you get a vertical asymptote for that. Okay, we're also going to do a few equations. Just got a couple, 3 of them here. We got one of them that's going to be calculator active. So whenever you're solving equations, this one asks for intersections of the graph. What do we do when it asks us for intersections? Set them equal, right? And so we will do 4 cosecant x plus 3, and I need to finish up here. We're going to quit after this. Well, we might do 6. We can do it pretty quick. I need to subtract 3. So I got 4 cosecant of x equals 8. And I need to divide by 4. And so I get cosecant of x equals 2. Cosecant is not on my unit circle. I could think of it from the unit circle, but I got to test a bunch of points, right? Which cosecant of x equals 1 over which function? Sine. So here's what you can do. It's called the reciprocal function, right? I could go through more steps to show you. But if cosecant equals 2 over 1, sine of x equals 1 over 2. You can just flip them there. What's happening is we're like replacing that with 1 over sine. Multiply both sides with sine, divide off. It'll just flip it. This will happen every time. So, can I find where sine of x equals 1 over 2? Oh yeah, we can do that, right? On the unit circle, that's your y coordinate. So it's right here, root 3 over 2, 1/2. And it's also right here, negative root 3 over 2, 1/2. And that is at pi over 3 and 2 pi over 3. So a lot like you were doing on your other stuff there. I've got them backwards. Pi over 6, I drew them in the wrong spot. Thank you. Pi over 6 and 5 pi over 6. Does that sound better? Pretend these are down lower. These should really be right here and right here. I'm going too fast. So these problems are a lot like the ones that you guys were doing with the sine and cosine and tangent. Just switch it to sine or cosine tangent at the end. There. So let's do this last one, and then we're gonna move on. The calculator one, you can just graph. You just graph them and see where they cross. That's all you do. It can do that for you. For this, I'm gonna have 3 minus 1/2 secant x equals 4. So I would need to subtract 3 here. So negative 1/2 secant x equals 1. And then I could divide by negative 1/2, or I can multiply by the reciprocal here, which makes it a little easier, because that's what you're going to do. So multiply by negative 2/1. So secant of x equals negative 2. So secant of x is 1 over which one? Cosine. So I can just switch, like this is negative 2/1, right? I can switch this to cosine of x equals negative 1/2. And where secant I don't know very well, cosecant or cosine I do know from the unit circle, right? So we are looking at x coordinates. This time we're right here. No, we won't. No, actually, we're not right there because we want negative. So we got negative 1/2 √3/2 at that point, and then we'd also have negative 1/2 negative √3/2. And so that is at 2 pi over 3 and 4 pi over 3, those two spots there. Okay. Questions? All right, you should not run into these today on the quiz. If you do, I've checked something wrong, so let me know if you see one that is secant, cosecant, or cotangent. You might see tangent, sine, cosine, tangent. Those will be on there. All right, so